recording started before we get too far off. I don't want to forget that. So Alex has been asking questions. Alex, do you feel better now about your answers?
I do, yes.
Okay. So I've had a few questions on 60 and 61. So just to make sure that we're all on the same page with that, 60 and 61 should be based on the analyses that you conducted. So that means the correct answer differs across you because it depends on what you found with your example data set. So 28 in this case was the population mean, and the decision that I'm asking you to make about the sample mean of the variable is, was it higher or lower? And that should be obvious just from the value that you found. So if you found a number that's under 28, it's lower, for instance. And then whether it's significantly lower or not significantly lower is based on the hypothesis test that you would have already gotten correct up here. So the t-value that you found that locates your result onto a standardized distribution, and then the p-value that goes with it. So for instance, question 35 right here is the p-value. So if your p-value is less than the predetermined alpha, which is 0.05, then that is a significant result. And if it is not less than 0.05, it's a non-significant result. So it's less than 0.05, meaning that if it is equal to 0.05, that's non-significant. And the same is true for mean GPA. Relative to a population mean of 3.6, was yours higher or lower? And then was it significantly higher or lower based on the hypothesis test? That was in question 35 up here, I think. Nope, question 41 for that one. So just looking to interpret the numbers that you should already have at this point.
Yeah.
The other questions are more general, and so those ones are not specific to your example data set.
Yeah. I found 62 amusing and some of the options listed because I was looking through it and I was like, wait a minute, these aren't even compatible. But I think, anyway, hopefully I'm not giving the game away or alternatively expressing my stupidity by saying, those couldn't possibly be related when people are like, well, duh, they are.
Well, they are related, and there is a correct answer in there, but it's not stupidity, it's inexperience. Just think of it that way. None of us is born knowing how to do stuff. We have to learn through trial and error. So if you don't have it yet, that just means you need more trials. That's all.
Yeah, which this was manageable.
Good.
I appreciate the way you structure this. It's better than using a textbook from 1981 that's been photocopied by hand.
Well, my goal is to get you ready to actually do quantitative analyses in your research. That is why you're in this class, and that is what I'm hoping to be able to train you to be able to start doing. All of the rest of it, doing hand calculations or derivations or things, do not directly meet that goal, and so that's why I don't emphasize them. There's a lot of jobs out there for people who are trained in quantitative methods, which is now data science, by the way. That's the new term for statistics. That's a lot cooler. And none of those job ads are ever going to ask for somebody who excels at hand calculations. Not a one of them is going to put that as a requirement. They're going to require you to excel at using software, because that's how it's done. So I'm glad that you liked it, and I'm glad that it's going well so far. All right, other folks, welcome. Homework questions is the topic for right now. Does anyone else have any that I can help with?
Yes, I have a quick question about SAS code.
Okay.
So I was wondering if you were like in a situation where you didn't need all of like the univariate data, if there was a way you could just like add code to the proc means to get your interquartile range. I wasn't sure if that was like a thing. I tried to look it up, but I was really confused, so.
To the best of my knowledge, that is not an option in proc means.
Okay.
So proc means has a subset of all possibilities. There may be other ways to get percentiles and interquartile ranges beyond univariate, but I don't know what they are off the top of my head.
Okay, thanks.
Sure. Yeah, there's about 17 ways to get a mean and standard deviation, but like the ones that are more esoteric are less common in the routines. any other questions? Okay, so this is due Monday night, and I just wanted to remind everybody that we are not meeting on Tuesday, the university holiday, are in lieu of spring break, so we'll be back here to start hopefully a new unit on Thursday, a week from today. So if you do have any questions on homework throughout the semester, you can always shoot me an email, things like, here's what I thought the answer was, and this is why I thought that, and I can help you. I can usually tell based on that piece of information where you're going wrong and quickly answer your question. Otherwise, you're welcome to come to office hours. So the way that I run office hours is in a group-based format. I did it the same way when we were in person. People show up, they work on their homework, and if they have a question, then I can answer their question right away, and then they can keep working, and that way I can answer everybody's questions at the same time. This class is very small. There's only 9 of you enrolled, but the other class has 30 people. So that's the easiest way that I've found to try and help as many people at the same time as possible. But you're all welcome to come hang out if you want. So, all right. Then that stuff. One thing on the website, I had not realized that the links I had posted to these 3 files for today were dead links. So I fixed those just before class. So those are things that we will refer to if time permits after we finish going through example 2 and lecture 2. So, all right. Then, usual question. Tell me what you remember from last time while we stare at a better beach.
We talked about using chi-square tests.
Yeah, what's chi-square for?
It's just like another way of like doing like a significance test.
Significance test to know what?
Is this the one where it works better with the nonlinear data distributions?
I think you might be thinking of Spearman's instead.
That's
Spearman's
probably it.
correlation. Chi-square is for a particular kind of variable.
Is it bivariate variables?
Bivariate means 2 variables at a time. Chi-square is for a bivariate association, but a bivariate association between what kind of variables?
Categorical.
Yeah, there you go. Categorical. Otherwise known as qualitative variables, factor variables, grouping variables, classification variables. Variables in which the numbers are just kinds. So they can be binary, they can be ordinal, they can be nominal. So yes, a chi-square is another kind of significance test for a bivariate association between categorical variables. So putting all of that together. Yes, indeed. So it's looking at contingency tables of how many times a particular combination of values was obtained in a sample and comparing that to how many values would be expected if the variables were not related to each other. And then a chi-square is a measure of the difference between observed and expected across all of the cells. So we looked at this. This is page 9 of example 2, how to do a chi-square in SAS. And then I wanted to make sure that we do the Stata version, since that's what you're going to get a chance to practice on homework 2. One of the things here. So do you want to go back over the SAS part, or do you feel good about that? Feel good? Feel good? So yes, proc freq. So frequencies is how you get, proc freq is how you get single frequencies per variable or cross tabulations. And then if you add the keyword chi-square, that gets you the significance test. The keyword expected gets you the expected frequencies. And so these expected frequencies, for instance, that are in the second row of the table are something I'm going to ask you to report for your homework as well. And so then last time we talked about how chi-square as the test statistic is a combination of the size of the relationship between 2 categorical predictors and the number of people in your sample. So it's both things put together. So to be able to talk about effect size, like what is the size of the relationship irrespective of sample size, one of the ways to do that is to look at the Pearson correlation between your 2 variables if they're binary. Odds ratios or risk ratios can also be used for variables that are binary or have more than two categories. And so then we ended with talking about a correlation between binary variables. A Pearson correlation you can always interpret as x goes up, what happens to y? A positive correlation means y goes up also. Negative correlation means y goes down instead. And what up means in the context of this table depends on how it's coded. So for instance, for the gender variable, it's coded so that men are the 1, women are the 2. So going up on x means talking about women specifically. So there's a little up for that. So note that in this little write-up right here, I have provided Pearson's chi-square that is right here. That's my test statistic. The p-value that goes with it. And then what's this thing in parentheses? Do you remember that? Why is a 1 there?
Degree of freedom, I think, right?
Yeah, degrees of freedom. And in this case, it's numerator degrees of freedom, meaning how many cells do you have to know to be able to figure out all of the other ones? It's not denominator degrees of freedom, which has to do with sample size. Chi-square doesn't refer to that. So if I have a chi-square that's a very, very tiny number right here, the p-value is a very large number, then this p-value would be compared to your preset alpha. So if alpha is 0.05, which is what it's always going to be this semester, then our p-value is non-significant. So putting all of that together, this analysis tells us that these two variables are not associated. If there was no association in the population, we would find an association this large 92% of the time. So well within expected fluctuation, and the effect size that goes with that test is a correlation that is pretty much 0. So said differently, the confidence interval around that obtained correlation overlaps 0, which means that the correlation is non-significant. All right, and so then this piece right here is something that I wrote just to drive the point home for you. That's not something that I would put in a paper. But this format of reporting a test, where you have test result, number, comma, and then the critical part, the end of the sentence, always has to put it into English for your reader. So my preference is either such that, indicating that, something like that, because this is the point when someone's reading your paper, that's the part they're going to highlight. They're not going to highlight the numbers. So a complete report of any analysis gives the stats, but then it puts the stats into a context as to what you've just found out. So just make sure that that's always part of what you're writing. So Stata, folks, the way to do the chi-square analysis in Stata is the tabulate command. So this one, if you list two variables, automatically gives you the cross tabulation. You don't have to have a star or anything between them. The comma cell is to get the cell frequency, so for each possible combination. So Stata splits the output into two different tables that was contained in one table in SAS. This table gives you the number of people in each of the categories, each combination, and it gives you the percentage. So 26% of the sample is unmarried men, for instance, and that's 197 actual people. So this table tells you what happened in terms of your data. What is the actual distribution of people across these categories? There is a separate command, tab 2, that you can use to do your chi-square analysis and to generate your expected frequencies. And so tab 2 then with the chi2, that's chi-square in Stata, by the way, and expected with these two options will get you all of the information that you need. So these two variables right here refer to the names of the columns. The comma says, okay, now what do you want to know about these two variables? And I want to know the chi-square test of association between them, and I want the expected cell counts. And so then it repeats the actual number of people, the frequency that was observed, and then it gives you the expected count. So this is all well and good, but unfortunately, Stata does not report expected counts to more than 1 decimal of precision. In the homework system, I require 2. And I have not been able to figure out how to make Stata spit out the second digit. So this is the one instance, one of very, very few instances in this class where I'm going to ask you to do a hand calculation to get the right level. I know, except that it's not by hand because you're going to do it in Stata because Stata is also a calculator. So those of you who are going to be using Stata to do homework 2, listen up. You're going to have to go through this extra step that is Stata specific. You're going to have to compute the expected frequencies to 2 digits of precision. So the formula, here's an example of how to do that. The formula is the number for the row times the number for the column divided by the total. So to get this number right here, I put in 363 times 397 divided by 734. So if you type display and then write out like what you would have typed into your calculator and hit and then run that code, it spits out the result for you. So Stata is your hand calculator. So do you feel better now? It's not actual hand calculations? Okay. So just because of my homework system, because I want 2 digits of precision for everything. So you'll have to do 4 of these for a 2x2 table in homework 2. The chi-square and the p-value is given right here. So it gives you chi-square with 1 degree of freedom. That's the value of the test statistic for association, and then this is the p-value, the probability of observing an association that large if the null hypothesis of no association were true. Turning on Stata whenever I need to calculate a tip now. Yes, that's what all the cool kids do. They break out their software. Absolutely. You can do this in SAS too, by the way, but you have to store the information in a data set and then print the data set. So it's a little more convoluted, but all right. And so then just to show you the second part to get the Pearson correlation between these 2 variables, I did PW core and then I got CI2, which is how to get confidence intervals around the correlation to get that additional piece of information. So there's the Pearson correlation between these 2 variables, otherwise known as the phi correlation that SAS spits out for you automatically. So, and I think that's it. So questions from the Stata folks? Yeah, no TI-84 calculators up in here. We don't do radians or degrees or any of that stuff. Like, it's gone. At one point, it was I was up in here and I could use the calculator to do shit like that. It's gone. It's long gone. Okay, any questions? Okay, so then probably by next week, I'll post homework 2 and you can dig into that. In homework 2, you're going to get a chance to do Pearson correlations, Spearman correlations, and chi-squares. So, and the same process in terms of I will give you a data set, I will give you starter syntax to help you import that data set and add all the labeling information. And then if you download the example 2 SAS or Stata file from the course website, make sure that I have that posted right here. That link, example 2 data files, then that will give you the syntax all in one place that you can borrow, paste into your homework syntax file and modify it to do the problems in homework 2. So everything that you need is inside there. You just have to figure out how to modify it to change the names of the data set, names of the columns, and stuff like that. All right. So any questions on this before we adjourn this example?
Just a comment that it took me like 5 minutes to figure out I have to run lines 1 through 12 in SAS every time. I was getting increasingly frustrated.
Yes.
But then I reread the example and I was like, there you go.
The same is true in Stata. So if you start a session, save your work, close out of it, and then restart another session, you have to execute all of the code to get back to where you were. It just opening the file doesn't put that information into the program's memory. You have to like activate it. So that is true in both. Okay, then a new beach picture. Let me go back to lecture 2 so we can finish that up. So I'm on slide 38 here. So summary of where we've been so far, learning how to get bivariate associations between different kinds of variables. So which test is the right one depends entirely on what kind of variable you have. So if you have a quantitative variable and you want to see if it relates to another quantitative variable bivariately, that's Pearson correlation to get an index of its linear relationship. If you have a quantitative variable and an ordinal variable, or a pair of ordinal variables, that would be Spearman. It works out to be the same thing as Pearson if everybody used every category. If you have categorical variables, that's Pearson's chi-square. And the combination that we haven't done yet, which is either an ordinal or nominal categorical variable with quantitative, that is best done with a model. So we will be getting there. That is going to be known as analysis of variance, by the way, which we will get to in a couple of weeks. So this whole process of estimating the relationship, testing for its significance, we can screw this up in two distinct important ways. So I want to introduce some new vocabulary for types of decision errors that can be made in the process of hypothesis testing. So significance requires having some kind of distribution to refer to, some place to take your results and put them onto a standardized way of talking about them that expresses how far what you found is from the null hypothesis that you expected. So we did this in Unit 1 talking about sample means. How far away is the sample mean from the population mean? Okay, let's put that onto a t and then we can assess whether or not the difference is unexpected or expected. The same thing with correlations. We get an index of the size of a relationship. We put that index onto a t to figure out if there was no correlation, so that'd be the null hypothesis in the middle, how far away it would be our obtained result. We just did chi-square, which is the test statistic that works for categorical variable associations, and then F is the other one we haven't met yet. That is going to work like a chi-square, but use denominator degrees of freedom. So for testing more than one thing at the same time and doing so while paying attention to sample size, that's going to be F. That's coming in several weeks, I think, still. And in each case, then we have our rejection region, as it is called. Where does unexpected start? Is it both sides? Yes. And what percentage defines unexpected? That's your alpha. So this picture down here then would go with the idea of a two-tailed test, meaning we are willing to accept both positive or negative results as being different than 0. And if we're using, say, a t-distribution that has infinite degrees of freedom, that becomes z. Then the cut point for where unexpected begins, where the 5% mark is, so 2.5% on one side, 2.5% on the other, that's a cutoff of 1.96 in this distribution right here. So if we have to make a decision as to whether or not what we found is too far away, too unexpected, then we're specifying a null effect and we have to specify an alternative. So alternative means, do we accept positive or negative or both at the same time? And we have two chances to get a decision correct in reality and two chances to get it wrong. So we have two different ways of screwing this up. First, there could be, in reality, in the population, no effect, so no relationship between two variables. And we could say, yep, I have retained the null hypothesis. The relationship that we found is sufficiently within expected territory, just like the chi-square result that we just had. And so that would be a correct decision. Or there could be no relationship in reality in the population, but we found what we think is a relationship. It's sufficiently unexpected that we say, yep, that's significant. It looks like these two things are related. That decision is a false alarm. We thought there was a relationship, but in reality there's not. And we know how often this is expected to happen because this is alpha level. So more vocabulary that goes with this idea. Alpha, more specifically, is your type 1 error rate. thinking you found something when in reality there's nothing to be found. That's a type 1 error, a false alarm. And so we set the probability that this could happen. When we say alpha of 0.05, what we're saying is that in reality, if there is no effect, we would find something this unexpected less than 5% of the time. Doesn't mean it can't happen, it just means that's infrequent. So if we were to do a simulation study, for instance, create two variables that are not related in truth, and then draw samples from them, we should reject the null hypothesis, think we found an effect 5% of the time. So we are deciding that a priori that a 5% alarm rate we are willing to live with. The other way that we can screw this up is what's known as a type 2 error. And so this applies when there is a relationship of some specific level to be found, but we don't find it. We miss it. So a type 2 error is a miss. It refers to not detecting a significant relationship. So you could make a type 2 error anytime that you retain the null or do not reject the null or say that a relationship is within expected territory. So that is another set of possibilities predicated on the idea that there is something to be found in reality. And so if there is something to be found and you find it, then that's a correct decision in this case. So by convention, beta is referred to as the type 2 error rate. Beta is also going to be regression intercepts and slopes in the models that follow, so it's unfortunate that the same letter gets used for both things. But more often, type 2 error rate is interpreted in terms of its opposite, which is actually a term called statistical power. So 1 minus type 2 rate is power. So power is this cell down here. What is the probability of actually saying the effect is significant if it exists in reality? And power is related to your sample size and it's related to your effect size. More is better for both. So what we worry about then is false alarms as well as power to find something that's actually there. Okay, with me so far? All right. So this concept is often taught using pictures like this one. I gotta be honest with you though, this confuses the hell out of me. So I made my own. The thing that this picture is intending to show is the trade-off between the two. If you increase your alpha level, so for a greater alpha, you are more likely to make a type 1 error, but less likely to make a type 2 error. So if you make it easier to get yourself into unexpected territory, you're going to have more false alarms, but you're less likely to miss something. If you decide to lower your alpha, so to go from say 5% to 1%, what that means is that you would expect a false alarm only one time in 100, but then at the same time you are more likely to miss something because you've made your cutoff more strenuous. So these things are compensatory. You can't win at both simultaneously. And whether or not a type 1 error or a type 2 error is more important depends on the context of what you're doing. However, even though type 1 error is set almost universally at 5% as a default, do you know what type 2 error is set at almost universally? What is recommended? Does anyone remember this from their previous coursework or research papers? It's okay if you don't. I'm just asking. It's 20%. By convention, we are okay with being 4 times as likely to miss something as to have a false alarm. So that 20% type 2 error rate corresponds to an 80% power rate. So when you design a research study, the typical advice is to shoot for 80% power, meaning that if there is something to be found, you will find it 80% of the time across repeated samples, which means you would miss it 20% of the time. So a conventional level of decisions is type 1 error 5%, but type 2 error 20, which is interesting. So I don't like this picture. I made my own. So here's how I want to try and describe the idea of type 2 errors and power, because it has nothing to do with the null hypothesis and it has everything to do with the alternative. So you can't talk about power and type 2 error unless it is very specific to the effect to be found. So just as we had a very specific null hypothesis of what we expected of 0, to be able to talk about type 2 error and power, we have to have an expected alternative hypothesis. So for instance, if I'm going to play God here to demonstrate this, I created 100,000 fake people, 2 quantitative variables, and I made them to have a population. So this P looking thing, do you remember what letter that is? A little bit of Greek quiz for you. Jerome gets extra credit for rowing his boat. Is that what this is? Excellent. I've never had anyone try to row their boat before in this class to do the Greek letter rho. That's very clever. But yeah, this P looking thing is rho. That's the symbol for the population version of the correlation. So in this case, I know what the right answer is. That's why people do simulation-based research in quantitative methods, is because then you know what you should get back. So correlation, in truth, is 0.3 between these two variables. I'm going to draw random samples out of my population of different sizes. And I have picked these particular sizes for a reason. I know they seem very arbitrary, but just give me a minute. I am going to draw 1,000 random samples of 42 people, 1,000 random samples of 63 people, and 1,000 random samples of 85 people. And then in each sample, I'm going to estimate Pearson's correlation, and I'm going to make a distribution here of what happened. So these histograms are individual correlation estimates from each of the 1,000 replications. So the picture on the left here is if I have 1,000 samples of 42 people, this is what actually happened. So in the middle here, the blue line I have flagged because I know what the right answer is. The right answer is 0.3. That's what should have happened. But in any one sample, I'm not going to get exactly 0.3. In any one sample, it went all the way down to almost negative 0.3 and up past 0.6. So if you don't have that many people, there's a lot more inconsistency in what the sample correlation is going to be in any one sample. That's the key idea here. So the idea of power is like, okay, how often would you reject the null hypothesis at this sample size given the effect size? The distribution gets tighter, less inconsistency as you get more people. So if I have 85 people, then the correlations vary from about 0 up to about 0.6. So there's less variance across these correlation estimates. Okay, with me so far? Still awake so far? Maybe that's a better question. We're awake. Okay. So then mapping onto this idea that in any one sample, you're not going to get the exact right effect size. You're going to get some wiggle around it. Then we can talk about type 2 error and power by taking these R correlation estimates in the top here and translating them into their test statistics, the T. So the role of T is to standardize what you found. So T is a function of the correlation estimate and the sample size. So this distribution right here are the T test statistics that go with the R's directly up above. And I have drawn in these red dotted lines for where a cutoff would be for where T is significant, which is just over 2 for 42 people. And so the samples in which the T would have been non-significant, so the T test for the correlation does not hit the unexpected territory, it stays within the expected part, that is type 2 error. So even though there is a correlation of 0.3, in all of these samples right here, I would have said the correlation is not different than 0. I would have said the correlation is within expected fluctuation, is non-significant, is retain the null hypothesis, is within expected territory. How often is that? 50% of the time. So the other 50% of the time, when we're on the right side here, those would be samples in which the t-test statistic for my correlation popped up as significant. It was greater than the cut point. That happened 50% of the time. So if I have 42 people and I am trying to plan a study in which I expect to find a correlation of 0.3, if I only have 42 people, only half of the time am I going to be able to reject the null hypothesis and say that I have a significant correlation. Okay, so what if I have more people? 50% of the time, I don't like those odds. All right, at 63, the type 2 error rate goes down to 37%. So in the middle picture here, only 37% of the samples in which the true correlation is 0.3 said, nope, not different than 0, no effect here. And the rest of them would have hit the cutoff to be significant. That's power. So power is the opposite of type 2 error. Type 2 error is saying that the relationship is not different than 0, even though it is. And power is saying, yes, I found something when I was supposed to, because I know what the truth is in this case. The truth is 0.3. If I'm willing to go up to 85 people, my probability of saying that I have a correlation that's significantly different than 0 is all the way up to 79%. Only 21% of the time in these samples, I would have said the correlation is not different than 0. Okay. And that would be the desired power rate. So in the social sciences, we shoot for power of 80%, which implies a type 2 error for missing something of 20%. Okay, how are we doing? Okay, I'm seeing some frowns.
Well, so for me, I'm kind of starting to understand now why so many people rip single case design, because like, I mean, it's the whole idea of single case design is predicated on small sample sizes because it's very hard to gather large populations of folks with very unique disabilities. And I'm just, oh boy, like just looking at this, I'm just, you know, we have such a small sample size and single case, and then seeing, well, how do we replicate that, you know, when we just have such a small size or whatever. And I don't know, I'm just having an existential crisis here about my whole field, but it's okay.
Well, no existential crisis needed, but I actually, to sort of address your comment, I have to borrow some stuff from my afternoon course, which is in longitudinal models. So in longitudinal models, you're sampling the same people or subjects or whatevers over time because you're trying to do both. You're trying to do like a single N of 1 kind of thing, and you're trying to generalize across people. So this same concept in single case land would refer to the number of observations within a person that you would need to collect to show that two things are associated. So let's say that you're studying problem behavior in children, and you want to know if a child is more likely to be disruptive on mornings where they skip breakfast. That could happen, right? It's called being hangry. Unfortunately, my child does not understand when he's actually hungry. All I get is hangry, and then he refuses to eat. But if I can get one bite of food in him, then all of a sudden he just starts shoveling because biology takes over. But let's say that you wanted to test that hypothesis that on mornings where your child skipped breakfast, they were more disruptive later in the day. Well, how strong of a relationship do you think those things have? If you think the relationship between those two variables translates into a correlation of 0.3, then you better survey that kid 85 times to be able to have an 80% shot at actually detecting that correlation. Now, what if there was a way to anticipate for any combination of sample sizes and any combination of effect sizes what you should get. Wouldn't that be cool?
I have a feeling you're going to blow our minds on the next slide here.
Yeah, there is. It's called one of two things, depending on how you approach it. But this is yet another case where people smarter than me have figured this shit out already, and we can use their work. So this is a handout that I linked to. I created this myself actually many, many moons ago to do a very simplistic version of what is known as a power analysis. So you can start with a target effect size and a target level of power and figure out how many people you need. So in the previous slide, this 42, 63, and 85 people, I did that because I wanted to point out these cells in the table. So for a correlation of 0.3, so going across the columns here, these are your effect sizes. So an effect size correlation metric going from 0.1 all the way up to 0.9. So first question, why aren't there any negative numbers for the correlation in this table, do you think? Because correlation goes from -1 to 1, with 0 being no association. So why aren't there any negative correlations included here?
I would guess because it'd be the same, just in the negative direction.
Exactly, because a negative correlation is just as strong. It just means as x goes up, y goes down. So nothing would change in terms of the math, how likely you are to find a negative correlation instead of a positive one. So you're specifying effect size in terms of like an absolute value here. So the values of the columns then are the effect size. The values of this row right here are your power rates, the probability of detecting that given effect size to be significant given your sample size. And so I've highlighted here the 80% row, and then these values, what we get if I have 42 people, corresponds to a power of about 0.5. If I have 63 people, that corresponds to a power of about 2/3. And if I have 85 people, that corresponds to a power of 0.8. And damn if it didn't work exactly like it was supposed to. This is where I'm like, wow, they got it right. I have no idea how they figured this shit out, but they did. It worked. So yeah, and if you notice a trend with the numbers here, at the same level of power, you need way more people to have the same probability of detecting a given effect to be significant if that effect is tiny. So let's go over here to the 0.9 column. A correlation of 0.9 would be like two things are like guaranteed. Like if I skip breakfast, I am gonna be a mess later on, guaranteed. If that relationship is that strong, 6 people, 6 observations, that's all it takes to have an 80% chance of finding that correlation. But as you move over, 783 would be what it takes to find a correlation of 0.1 80% of the time. So these percentages refer to repeated samples of the same size. Okay, is this making sense so far? Okay, so this is power analysis when you start with, here's the effect size I'm looking for, here's my power rate, how many people do I need? That is not how it works in the real world. Because if you knew what effect size you were looking for, why would you do the study? Right? This is information that you probably may not have, because why else would you be invoking this research project? So what it actually ends up happening, I work a lot with researchers who are writing grant proposals. Have any of you had a chance to help with grant proposals yet? Not yet? Oh, they are such fun. Oh my goodness. Not. Every grant proposal that has some kind of data collection effort, they're going to want you to do a data analysis plan. What are you going to do with the information that comes back in terms of the statistics? And they also want a power analysis. This sort of idea. And people come to me. They do not come to me with an effect size. They come to me with their sample size. They say, I can afford 100 kids. What can you do with that? Okay, thank you for being honest. That is a sensitivity analysis, by the way. That is not a power analysis. And so, but I do the same thing. I'm like, all right, so let's shoot for power of 0.8 because that's what NIH wants. Sure. And you said you can get 100 kids? Okay, that's going to get you a correlation somewhere around, let's go with 0.27. And then I write it up. If they came in and they said, I got 50 people, I'd say, all right, that's going to buy you a correlation of 0.4. And I would phrase it as, at the planned sample size and an 80% power rate, the minimum detectable effect size would be, say, 0.4 if it's 50 people, about 0.27 if it's 100 people. So you can work either way from this table and anticipate to what extent you need as many people as you do. This table is a very sort of simplistic approach. Most of the time what I have to do is much more complicated. It involves actually making up data that would be consistent with a particular model and then seeing what the effect sizes that come out of the model would be. But it's still based on the same sort of principle. How often would you find a significant relationship that's this big is predicated on effect size and sample size, where both of those lead to higher power, lower type 2 error rates. So have I blown your mind with this? Maybe? I know. So there are programs that you can use. There's G-Power is a big one. R has 8,000 different versions of power analysis built into it. SAS has a power thing. I can give you examples on how to simulate data to do power analyses if you're ever in that situation. So this is a thing that you would want to be able to do for any analysis that you are planning for research purposes. Either pick a good sample size if you have that choice, or else justify your sample size. I once had to write a sample size grant application for somebody who was doing clinical, not clinical trials, but like randomized control trial type things. But they were doing it in schools. And they wanted to assign a school to be a treatment school or a control school. And I was like, okay, so how many subjects are you planning? And he's like, oh, well, we're going to have like 30,000 children. Okay, not relevant because you're assigning schools to treatment or control. How many schools are you going to have? Oh, 5 in each group. Okay. And so then I had to write, we have 80% power to detect a correlation of positive infinity. Like, because with 5 people in each group, you have no shot at finding anything. The effect size has to be enormous to be able to have 80% power. So that's what I wrote down because they weren't going to listen to me. So, anywho. So summarizing then where we've come so far, and then I want to show you the example thing. So every hypothesis test that we're going to do this semester is going to have some kind of estimate of a parameter, if it's from a model, some kind of test statistic. It's going to have numerator degrees of freedom and or denominator degrees of freedom to be considered. Everything's going to have a p-value. And you also want to have an effect size, because any test statistic is a combination of sample size and effect size. So we got to pull those things apart. Conditional on your decision about significance, what can happen? So if you reject the null hypothesis, meaning you think that your relationship is significant, you think you found something that's well into unexpected territory, given your alpha level, you do have to worry about type 1 error. So if I have a correlation matrix, say of 10 variables, that's a lot of different correlations I'm reporting. If I pick an alpha of 0.05, that means 1 out of 20 of them is going to be significant just by chance, even if there's no relationship there. So if I want to be appropriately concerned about limiting my false discoveries, my false alarms, I might pick a lower alpha. So if I go from an alpha of 0.05 down to 0.01, then I'm saying only 1 in 100 would be expected by chance. I can live with that. In doing so, though, if I make it harder to say I found significance, I'm also making it more likely to have a type 2 error, to lower my power. I'm more likely to miss something if I increase the standard for what significant means. So there's always a trade-off. You do still have to worry about power to some extent. So this table, for instance, if I have 8 people in a study and I have a correlation that in the study of 0.5, I could find a significant correlation with 8 people. How often would I find that correlation though? 25% of the time. So I could get lucky. And these sorts of results where you find something to be significant, even though power is not in your favor, those are the ones that people are more likely to be concerned about in terms of replicability. If you get lucky and you find something significant, even though you have shit for power, you may have to go to extra trouble to defend that. Or just to be appropriately cautious in talking about it and saying that, yeah, we need to make sure that we replicate this finding in other studies, because any result based on 8 people, even if it is significant, is probably not that reliable. On the other side of the coin, if you retain HO, if you say that your result is non-significant, that you don't have a relationship that's different than 0, then you got to worry about power and type 2 error. You don't have to worry about type 1 error because you haven't made one. And so when you're in the position of trying to advocate for the null, like you want to show that 2 things are unrelated, you have to be prepared to defend yourself to say, no, I have very good power to find something. It's not that I have no power, it's that they're really not that related. And the best way to be able to do that is to refer to the effect size, to say this effect size is so small that I'd have to have 1 million people to have decent power to find it, therefore it is not practically meaningful. So if you say you haven't found something, be prepared to talk about power at some point in the review process. All right, the end. So questions or comments on that?
For your power table, is there a recommended R that you should shoot for? And so like look at just the right side of the table, or is there any sort of cutoff that you should stick to?
I think it is entirely context specific for your research. You have to be prepared to argue that that effect size is meaningful and possible. So in the example that I gave a few minutes ago of having power to detect an R of positive infinity, the reviewers rightly pointed out, like, why are you expecting an effect size that huge? What are the odds that you would actually find an effect that big? We wouldn't. So it's not a meaningful analysis in terms of power. So it's not like there's an effect size that's necessarily like enough. It's just, is it likely to happen in your field? What have other people found when they're studying related problems? And if to the extent that you can go off of what other people have found, then you have a leg to stand on. So the further left you go, the smaller the effect is, the less practically meaningful it is. But even correlations of 0.1, if we're talking about, saving people's lives or things like that still matters, right? Or keeping my son from being sent home from kindergarten, it still matters. True story. He got kicked out of preschool 3 times. What kid gets kicked out of preschool? Mine. Because he couldn't handle himself. Jen, did you get kicked out of preschool? And you turned out okay. All right, good. So I don't have to worry then. Yeah, the first time it happened, he told us, I just wanted to go home. Oh, well, we're not going to have any fun today. So we actually brought him into the office. We brought him into work and we made him sit there. And I had a workbook of, letters and numbers and shit. And I'm like, no, you're going to sit here and do your work because this is a school day and mommy has to work and you are not going to have any fun. This is not going to be a thing. But Anyway, I'm off on a tangent. Did that answer your question, Emily? Yeah. Okay. Any other questions or comments about power? Or preschool delinquency? Take your pick. Okay. Then if not, I wanted to show you something. An example of why power and effect size matters in real life, so to speak. This is the article that I had linked to. This is a story from my past. So I was a psychology major as an undergraduate. I took a senior level class on motivation and emotion, and we had to do a project in the class where we had to pick some area of research and write a term paper about it. So this was in the late 90s, and the book Emotional Intelligence had just come out. Have you heard of this before? The idea that you can have IQ and you can have EQ as a different set of intelligences seems very reasonable. I was interested in the topic, and I was reading the book, and they cited research by these folks right here as to why emotional intelligence is something that matters and is something that we should pay attention to in children. And this is the basis of the marshmallow studies. Have you heard about these? Delay of gratification. So this is some research from that line. The idea is that they had an experiment with 4-year-olds where they put a marshmallow in front of them and said, I'm going to leave the room, and if you cannot eat the marshmallow while I'm gone, I'll give you 2 of them, or I'll give you 3 of them. There's a whole bunch of studies. And the results reported in the book were that children who were successfully able to not eat the marshmallow while the person was gone ended up with higher ACT and SAT scores. So delay of gratification was something that was somehow supposed to be a protective factor or indicative of future success, right? So I went to the original source, this paper that was reported in that book, and I found something that my little brain couldn't handle, because I was learning about correlations and power and effect size in my stats class, and I came across, let me try and get to it here, the scroll is very slow, a table. I have it highlighted here. Sorry, the zoom and everything is killing my computer's speed. Keep going. I'll get to it. I know I'll see it right here when it's... Okay, it's not highlighted in this copy, but it's right here. This table. So, oh, it is highlighted. Thank goodness. So this table reports correlations between delay of gratification. So it's measured in like the response time for how long it took them to eat the marshmallow, and if they didn't eat it, they put in the maximum amount of time. There's issues with that, but that's beside the point for this class. And then how correlated those response times were with subsequent SAT scores across 4 different conditions of the study in terms of the instructions that they gave the kid with the marshmallow. And this first column right here, 0.42 with the star and 0.57 with the star, those indicate 2 different cutoffs in terms of a significance level. I hate that, by the way. It's like, get off the fence. Like, pick your alpha and just, it's either significant or it's not. But anyway, these are the numbers that they made a big deal about in this paper in the book, meaning that a positive correlation here. So the longer that they were able to not eat the marshmallow, the higher their subsequent SAT scores. Okay, but what about this number? What about this correlation in this other condition that's negative 0.4? Why aren't we hearing about that number in the book? Because in that condition, the people who waited longer to eat the marshmallow had lower SAT scores when they were older. Why am I not hearing about that number that contradicts this finding? Why aren't there any stars next to that number? Anyone want to make a guess?
The p-value was just too high, according to these, that if it fell in these ranges, it should have a star next to it.
That's right. So the p-value that corresponded to that negative correlation was greater than 0.05, which is why it is unstarred. But how could that be? Why is a correlation of 0.42 significant, but a correlation of negative 0.4 is non-significant? What else goes into the declaration of significance besides the correlation itself? Where does the p-value come from?
The sample size is significantly smaller.
Yeah. So these are 4 different sets of kids that they tried to contact, many years after the study was conducted to try and get their SAT scores. And for whatever reason, the kids in these conditions did not respond at the same rates. There's only 14 kids and 12 kids. So even though the relationship is almost exactly the same size in the opposite direction, this one was not interpreted or reported because it was non-significant. And it was only non-significant because it was based on half the sample size. So this was what my paper ended up being about, by the way, in undergrad. I was like, they cheated! Not cool! But yeah, don't let the stars fool you. The test statistic that labels these correlations as significant or not is directly a function of the correlation size, the effect size, and the sample size. So you gotta know both. It's not just whether it's significant, but what is the effect size. So if I only had 14 people, how often do you think I would find a correlation of 0.4 to be significant? Let's answer it. This is D. The R one from the handout is over here. The answer is like 0.27. Right? That. So an R of 0.4 for 12 people has a power of 0.25. So I have 14 people, so it's a little higher than that, but still. Only 25% of the time, if the true relationship were 0.4, would I find it in a sample of 14. Whereas their sample of, say, 35 or something, that translates into a power of 2/3. So a much higher probability of finding the same relationship to be significant if you have 35 people than if you have 14 people. So this is why it is imperative in describing your results to not stop at the word significant. For every p-value, there should be some kind of effect size that goes with it, because that has to place it into the context of just how strong an association actually is. When you are doing a correlation, the correlation is the effect size. Like, that's super easy. That's what you report. What if you do a chi-square? If you're doing a chi-square analysis of a bivariate association of 2 categorical variables, you don't get an effect size directly. You got to take the extra step to go and ask for it. So for a 2x2 table, you can turn your chi-square into a correlation. You can also turn it into an odds ratio or a risk ratio or other things too. So there's an extra step involved in making sure that you have a complete reporting of the findings. So significance and effect size all at the same time. All right, so the other effect size, by the way, that's in this handout that I gave you is in a different metric. It's called D. You heard of Cohen's D before? It's a standardized mean difference. So this is a more useful way of thinking about effect size when the effect in question is a group difference. So how much... Go ahead.
Is that the same as Cohen's kappa?
Nope, that's a different thing. Cohen's kappa is a measure of association that takes into account how frequently you would agree by chance. Same Cohen though, I think. Cohen did a lot of things. So like this would be more useful if you're planning a treatment study and you want to anticipate how much better your treatment group is going to do than your control group. So these are in standard deviation units. So we'll see D in a few more weeks, but this one, for instance, a D of 0.5 means that your groups are half a standard deviation apart. So it's another way of looking at it, and the same principle holds. The smaller the group difference, the more people you need to find it to be significant. D isn't bounded by 1 though, because you can be as many standard deviations apart as whatever. So positive infinity is the limit there. All right. So any questions on any of this stuff?
I just am curious because, so Emmy and I are actually in the same program. We're in the counseling psych department, and we see Cohen's D quite often in psych research. And so I've actually never even heard of R being a measure of power. I'm just wondering how often that is like actually used in like, practice.
So R is, you can think of it as a metric of an effect size. R describes effect sizes in a correlation metric that ranges from -1 to 1. You may have heard of it also as eta. R's and etas are the same idea. D is related to R. There is a linear transformation between, you can go back and forth. I don't think I have that handout open, but that's the other one I put, is a link to conversions across these things. You can go from a T to a D to an R to a chi-square to an F. They're all related to each other. You may also see versions of Cohen's D that have various corrections. Like there's a G version and an H version. Like people have come along and tweaked it and put a new letter in front. But the metrics are all in the same. It's in some kind of standardized mean difference. So the other thing you may have seen is like an R square effect sizes in terms of variance explained. That is literally R squared. That comes into a play when you're talking about a combination of variables relating to an outcome as another way of talking about effect size. So is it Emmy or Emily? I just caught that.
Either one's fine. I go by both.
Okay, because it says Emily under your name, which is usually like what I do here.
Yeah.
But...
I keep Emily on my Zoom since I see therapy clients, and then it matches my email, so it just makes more sense to them. But either one's fine.
Gotcha. Okay. Well, I didn't want to be screwing that up the whole semester and have no one tell me. All right. Does that help at all, Doris? So Doris, and yeah, so R is really, really common. But if it's in the context of trying to find a therapy effect, like if it's relative to a group difference, then D is a much more natural way of talking about that. All right. Other questions? Okay. Then a week from today, we get to start talking about new stuff. We are heading into the world of models. So leaving behind bivariate statistics and learning how to actually predict variables from each other. That's where we're headed next time. So simple linear regression and analysis of variance is where we're headed into, in case you're familiar with those terms. All right. Anything else before we call it a day? You love regression? Me too! We're going to do some cool shit. It's going to be exciting. And we're all going to do it in SAS and Stata. Also, that will make it even more exciting. So, all right then, let me know if you need anything. Otherwise, I will see you in a week. So enjoy your time off. Bye for now.